Okay, yeah, so we've taken a deep dive into classes. We introduced the class structure, constructors, access specifiers, the default, synthesized constructor. We got an idea of how constructors work. We also found out that if we have more than one constructor with different constructor arguments, then we have what's known as constructor overloading. And then we can have a constructor, call another constructor, and we can pass classes to free functions, and we can return class objects from free functions. And then we introduce this UML class diagram. For object-oriented programming, UML has a lot more diagrams, but I just focus on the class diagram because since this is an introductory programming course, I mean, I don't want students trying to learn UML, so it's just a simple diagram that just shows us how classes interact with each other. We talked about this pointer briefly, static variables, free function, friends of classes, object composition, meaning a class that uses another class as a variable, private functions. We've still not talked about this, guys. Well, we will eventually. And then we created a vector of bank account objects in the ATM, class friends of classes, explicit constructor, and operator overloading, right? So that is actually a lot of concepts for object-oriented class development, right? Or today we talk about pointers. So if you've been lucky enough and you've talked to people that have had a bad experience with C++ or unlucky, right? They will tell you that pointers was their downfall. But mainly because it's very difficult, like to understand the pointers and deal with dynamic memory, use the memory, release the memory. How do I clear it in functions? How do I release memory in classes? Well, we'll take a step at a time. I will introduce pointers today, and I'll show you how to create dynamic memory with a pointer, but then I'll also do a 180 and tell you that in this class we will focus on unique pointers. And a unique pointer works like the string and the vector. How? Well, the concept is developers created the functionality within the class to create dynamic memory, use it and release it. Okay, so we don't have to worry about that. However, I do have to introduce pointers, and I do have to talk about dynamic memory. Mainly pointers, like I said, they'll help us with inheritance, which we'll cover next week, and polymorphism, which we'll also cover next week. Okay, and those are advanced object-oriented programming concepts, and actually those complete the 4 principles of object-oriented programming, right? Encapsulation, abstraction, inheritance, and polymorphism. Okay, so we got 2 more to go. Okay, so I won't just throw you into the fire. I'll remind you or give you an overview of what references or how references work, okay? Because references and pointers, they're kind of like cousins. So if you understand references, then you should hopefully understand pointers. Okay, let me check this in. I think I used you all's repository, right? That's okay, then I'll have to use theirs. Okay, what's today? Wednesday, right? Wednesday. Close folder. I guess we'll have to use this one. It's okay, it's the same code. Okay, so for this examples, we have to go into module 9. So SRC examples, CMake list, module 9. remove the pound sign so that CMake recognizes it is a source code folder. And then we do the same thing to test examples CMake. So now we should be able to compile those and write test cases. So I go here. Okay, so we should have module 9. Yep. So let's go ahead and create the first example. And this is just a refresher for references. So if you missed them, this is your second chance to catch them, okay? So let's see here. Create a ref function with reference and pointer parameters. So we'll say void. And we'll say ref pointer. For now, we will just add a reference parameter. Like this. So this should be familiar to us. Then we go into the CPP and then we write the code for it. This is not a class, okay? So these are free functions. So we're not creating a class. And then in here we can say num equals 10. We can go into our test case. And include ref pointers, test case, test the reference parameter. Okay, so we'll say int num equals 0. We will call the ref pointer function. We will use num as a parameter, and then we'll have to determine what n is. Okay, so anyone, what is the value of num after this statement executes? Num is 0, and here we say num is 10, so which one wins out? 10, right? So it should be 10 here. And we will go ahead and execute our test case just to validate that. And it's taking its time, so it's finally linking. Oh, I think I need to found out that if I turn off the virus real-time protection, that helps it somewhat. Okay, so green is good, up arrow, space, dashes, enter, and it is 10. Okay, so we should have known that already. Okay, so we have the test case, we have the number equals 0. We call that function ref underscore pointer. We use num as the parameter, and we have our stack memory and so forth. So then we are like, okay, you get this slot, and when the function executes, the parameter references that address, and when our code executes, num equals 10, it is actually going to modify this one. So the value of this one now changes to 10. And that's why our test case is successful, right? But this is the diagram for that test case. Okay, we kind of knew that already. Let's go into main and query the reference. just as reminder. Okay, so using cout, we say okay, int num equals 0, num 1 equals 5. Values don't really matter. And then we're like, okay, let's create a reference that points to num. And then we are like, okay, value of num, num. Address of num. When we want the address, we should know by now that if we use reference, it returns the address to us. So then we can do that. And then we can also say value of num via numref. Value of num via numref. So that should be numref, right? And we can run this. Okay, so let's go here and run that code. So value of num0, it's an address ff04, and the value of num via numref is 0. Okay. So when you create a reference, you can only assign it one address. If you reassign it, try to reassign it to another address, you can't do that. However, the compiler will not alarm you or give you a warning or mark it as a syntax error. What am I saying? We can go here and we can say numref equals num1. And notice usually, like, if something's wrong, then we get some underscore. Here we're okay. What's this underscore? Is just telling us that we're not using num1, but that's okay. We will use it eventually. So then we're like, okay, so what is the value of supposedly num1? Because according to this statement, we are trying to reference a different address. So let's see what happens. Run. So let me see here. Value of num via numref. Numref equals num1. Well, actually it should be 0, right? So let me validate this again. Numref. What happened here? I just ran this example yesterday. Am I seeing things? No, it's a 5, right? I see a 5. Let me see here. Address of num1. Num1. Okay, and then let me get the address of numref. The address numref is pointing to. Okay, let me run this. Okay, so nobody replied, so let's run this. Let me put a new line here. Okay, address of num1 is f04. Okay, I know what I did wrong. Okay, so what happened? Anyone? Can someone tell me? I just kind of lost my train of thought for a few seconds there. So five, right? So we got the value of num1 5. What's num1 5? What's num0 0? So if we go into the diagram, this value, actually I haven't diagrammed that code, so let me diagram it. So we have int num equals 0, num1 equals 5, and then we had the diagram for their stack, and we know that this is 0 and this is 5, some large number, and then we said create a reference point to num, and then later on we say, well, num ref equals num1, but this value is changing the value. So it changes this one to 5. So yeah, we just did that, right? So here num1 changes the value of the reference that num ref points to, which is num1, right? So if we look at the diagram, this one changes to 5. Okay, so what if we try to do this? So now it's like, okay, you can't do that, but we shouldn't have to do this, right? Because notice over here we didn't have to put an ampersand or a reference operator. So when we do this, then we are not reassigning addresses, we're just changing the value. Okay, so it's very important to remember this. References cannot change, right? We already married these guys, and C++ believes in the holy marriage, right? So once they're married, they're stuck together forever, right? So numRef will always point to num0. So if we finish this diagram, we're like, okay, you here, you here, you point to that guy, and then when this executes, we are changing the value from 0 to 5. Okay, so that's what's happening. And num1, it's still 5, like we didn't mess with it. Now you cannot use num1 to change the value of num, because they are different variables, right? Here what we did is we just got the value num1 holds, which is 5, and then told numRef, whatever you're pointing to, put that 5 in there. Okay, so now what? So you can create a reference, it can point to a variable, you cannot have it point to a different variable, and I guess that's okay, but the pointer can point to one variable, and then you can have it point to a different variable and to a different variable. Like, it doesn't have a limit. Like, you can just have it point to different variables as long as it's the same data type. Okay, well, if you want to make the coding easy. So that was, so this is references, right? So the key, so how do we know? So this one, what's this? Address of num1. And then this is not the address of num1, this is the address of num then, right? How do we know? Here, and then over here, notice we're saying the address of num is F08. The address of num1, or actually num, is F08, and here num1 is Let me run it again so that we can visually see that. Originally, num is F08. It'll be there until our program exits. Num1's address is F04. However, we thought we were trying to change the address. Instead, we changed the value. So notice that the address of num via numref is still F08, meaning numref is still pointing to num. So now we should see that, oh, okay, so you can't change it. You can't change what it points to, it being the reference, okay? Now a pointer, also one more thing, remember a reference does not get its own address space. A reference is just a clone of a number. It does not get its own address, but a pointer does, so that's another difference. And with a pointer you can create dynamic memory. So let me create an example. What's this? Num2 equals 10, oops, equals 10, num 3 equals, let's say 15. And then we are like, okay, create a pointer. Create a pointer to num2. We have to use the address operator always when we wanted to point to something, okay? Meaning, hey, give me the address of 2. Okay, so we do that. And then we can start asking it questions like we did over here, okay? So we can say cout value of num2, and then address of num2, we use the ampersand, and then we say value of num2 via num pointer, and we'll diagram this too, okay, so that y'all can see how that's in memory. So value with pointers, 100% of the time when you want to get the value of the variable it's pointing to, you have to use the asterisk. If you don't, it's gonna return the address. It's gonna give you the address, okay? So here I'm saying the value that pointer points to. So we say, okay, num pointer, that'll give me the value. And then we say, okay, so how about the address of num2 via num pointer? And like I said, if we do not use the asterisk, if we just do num pointer, then that returns the address of the variable that it's pointing to, okay? And finally, well, let's run this, okay, and then we'll do the finally. Okay, right here, yeah, okay. Okay, so okay, let's hold off on running this, okay? So we won't add to the diagram, right? We'll create a different one so that we just focus on the pointers. So let's add a page here, and then we'll say, so this is the pointer, right? Okay, so we have int num2 equals 10, num3 equals 15. So we know this will be 10 and this will be 15. And then we are saying num pointer equals ampersand num2, or the address of num2, right? Okay. Where does that one go? Its own space and memory, right? And if we understand the stack, then we know that it's sequential, so the next available free space is 92, right? So then we can take this out, and then it comes here. Okay, so then we are saying save the address of num2 into your address space. Okay, so num2, this blue one, 100, right? So we'll say x100, right? So we won't get confused with values. So we'll say this one is holding x100, and then we can draw an arrow like that just to show that it is pointing to that address. Okay. Any questions here? Again, we still recall that all this space right here would be like the main memory space, right? Main gets its own space. So all of that is within the main space. For now, we're assuming we're not working with references, right? I didn't want to put them in the same diagram. Any questions? Okay, so let's see if we can validate that this is happening, meaning the pointer gets its own memory space. Okay. Yeah. So the way you read this is a pointer to integer, and the name is num pointer. So then we point to an integer, right? So, yeah. Okay, so now let's see how we can get the address of num pointer, and well, maybe if we use that guy. Okay, and then we go ahead and execute it. Doesn't look too good. Let me do that and that. Okay, so we are wanting to focus on num2. So the value of num2 is 10. The address of num2 is FEFC. The value of num2 via num pointer is 10. The address of num2 via num pointer is FEFC. And notice the address of the pointer itself is FEF8. Okay. And this one's 0, 4, right? 0, 4. FF04, FF00, okay. FEFC. So notice that the pointer gets its own address space, but then it holds the address, and then we can go tell it, hey, go to that address and get me the value. And the way we do that is with the asterisk, right? So again, this returns the value of what? The value of num2. So we come over here. When we say asterisk, is like in x100 there's a value, go find the address first and then give me the value. So then we get the value 10, okay? Yeah, it's the same like the reference. I mean, syntax-wise. And then if we just say num pointer, then what we are saying is just give me the value at address 92, which is an address x100. And finally, if we say reference of num pointer, then we are saying give me the address where you live, and it's x92. Okay. Any questions? So references and pointers are cousins, but one has a lot more functionality, right? And with pointers we can create dynamic memory and what have you. What's the use of pointers, right? So we can create dynamic memory. We can use that dynamic memory to implement inheritance and polymorphism. We've not talked about inheritance yet. We've not talked about the concept of polymorphism. Why? Because we need to understand pointers first before we can jump into those topics, right? So it's the foundations for those concepts, right? So we will create dynamic memory today, but we won't use it to implement inheritance or polymorphism. Those will be introduced next week. Okay, so let me see here. We go back to our original example. Create a function with reference and pointer parameters. So we've got one piece, and I didn't want to write the whole function until at least I showed you how pointers work. So now we can go in here and say, okay, so a pointer to integer num1, and I have to go and modify this piece here. So a pointer to integer num1, and then I'll say num1 equals 20. Come on. Okay, you see, I'm violating my own rules already. Well, not my own rules, my own preachings, right? So I want to change the value, so then I need to use an asterisk, right? So I'm saying here change the value from whatever it is in num1 to 20, right? So, and then we go back into our test case, which is broken because we need to make some changes here. So then we have num1 equals 0, and then here we will say, okay, so pointer, regular integer, we need its address, so then we say reference num1, or the address of num1. And then we can go ahead and create the assertion for that one. So num1 should be equal to what? 0 or 20, 50-50. It should be equal to 20, right? So that was Anthony, right? So so 20, and we run the test case just to validate that. So run. And while that's running, what we can go ahead and do is come back here and then go ahead and modify this code to match our test case. So we'll eliminate that, put a comma here, num1 equals 0, and then remove that and that, and here we say the address of num1, and then we go ahead and that's also 0. This right here is the main. So that's the memory allocated to the main function, right? And for an instance, when ref pointer is running, ref pointer will get its memory, right? And in there, assuming that the compiler gave our pointer this lot, so then what goes in here for the second parameter? It's pointing to something. So what is it pointing to? To num1, right? So num1 is in x96, so then this one would be x96. And when our function executes, we are saying, I think, change it to 20, right? So then this one changes to 20. And when the function exits, then this region of memory here will be released, right, from memory, and main will still be in memory. Yeah, address of num1, which is 20. So that's the diagram for that function we created with a reference parameter and with a pointer parameter. Any questions? We have to say the address of num1 because pointers, when we want them to point to something, we have to give them an address. So what we've said here is a pointer to an integer, num1. So if we wanted to point to something, then we have to send it an address. And with the reference parameter, I mean the reference symbol, we can get that address. That's why we have to use the address operator here to get the address of num1 and feed it into the pointer, and the pointer saves it where? In its memory address, and then we know that it will instantly, while the function's running, it'll point to that num1. Okay, so interesting stuff, right? All we've known so far is, oh, a pointer works like a reference. The difference so far is that a pointer can be reassigned, or can it, right? Well, we not tested that, right? So now let's go ahead and see. Okay, so now we can say, okay, so here I told you to point to num2. We queried you, we asked you questions, we saw the output, and yeah, you're pointing to num2. Go ahead and point to num3. Again, remember, we wanted to point, meaning we wanted to get the address of num3, so then we have to use the address operator. So now we are saying, hey, point to num3 now. And then we can, without going through all the hoops, we can say, okay, so value, oh, why not, right? I'll just copy and paste and modify so that I don't have to go through everything, type everything again. So this one should be 3, 3, 3, 3, and then we say 3 here and 3 here, and let's see what we come up with. So let's run that example. Okay, so this last 2 blocks. So num2 is 10, and it was pointing to ff00. We ran this statement right here, and then we started asking it questions with cout. So now we know value of num3 is 15. It is 15. It's an address FEFC3. The value of num3 by the pointer with this statement via the pointer, actually with this statement, is 15. And then what is the pointer pointing to? Well, address of num3 via the num pointer is FEFC3. And then maybe we should diagram this, right? So any questions here? So now we know, oh, I can point to a different variable, which is good functionality, but unfortunately it can lead to errors, right? Because if that pointer is pointing to dynamic memory, and maybe another pointer is also pointing to dynamic memory, and the programmer deletes the original pointer that created dynamic memory, that memory is gone from the heap, the second pointer is now pointing to invalid data, right? So that's a dangling pointer. I mean, we left it hanging. So it comes with its issues. And with a pointer created memory dynamically seems easy. Create dynamic memory, use it, release it. But this use it piece, the scope can be small or large, and the larger the scope gets, the harder it is to determine when to release the memory. And then if we forget to release the memory, then we are leaking memory. So then that's a memory leak, right? So let me diagram this piece, okay? And we'll use this same diagram, this one right here, or not. Let's see here, not this one. Where's the other one? Pointer, yeah, this one. Okay, so we're ignoring all the reference code, right? We're just dealing with pointer code here. So then we are like, okay, num pointer equals to the address of num3. Okay, so right now pointer is pointing to x100, but now we are saying do not point to x100. Point to x96. So then this one is gone, and now it's pointing to that one. So one of the use cases is when you create dynamic memory and 2 pointers can point to that dynamic memory, right? That's like a very simple use case. Or you create dynamic memory in a function, you return the dynamic memory, and another pointer points to that dynamic memory, right? So that's also a use case. Or our function arguments too, right? Like when we send in a pointer, then we initialize that pointer, and then in the function we can create another pointer, right? But mainly the main use case for pointers is for dynamic memory, right? Like create dynamic memory in a function, return it. You need a pointer in the local function to create dynamic memory. But then when you return it, it has to be saved somewhere, so you have to save it to a different pointer, right? So, okay, any questions? Interesting stuff, right? So hopefully now you understand why I leave pointers toward the end of the semester, because pointers are the foundation for inheritance and polymorphism, which we'll cover next week, for dynamic memory, for creating dynamic memory in functions and releasing them properly, and also in classes and knowing how to release them properly, right? So we'll get into that in a little bit when we talk about the string class. Okay, let me go back to the agenda. Okay, so I think we're here. So dynamic memory example. How do we create dynamic memory? And we'll do it in main. Again, not writing test cases here. I mean, I wrote the test case for the pointer, but I want to make sure students understand how pointers work, right? So that's why I'm writing the code here in this main piece. Excuse me, dynamic memory. So if if you recall, I've talked about the string and the vector and how dynamic memory is created for us behind the scenes. Developers created some code that writes that creates dynamic memory for us and stores that memory, that data on the heap. So let me go here. So dynamic memory is on the heap, right? And then there'll be a pointer on the stack pointing to the heap, right? So let's go ahead and write this code. I will say a pointer pointer num equals, and then when we create memory dynamically, we have to use the keyword new and then the data type, and then we can initialize it to some value. Here we are creating a integer with dynamic memory for it, meaning where's the value stored? Well, the value will be stored on the heap. So if we go ahead and diagram this, here as some address and then some other address, whatever, right? So then remember, the stack is sequential, meaning the next free slot is always taken up, right? So assuming this is the next free slot, then this is our address, and then assuming the 5 was here, then we will be storing the address number y40, and then we just draw an arrow just to show that we are referencing that value on the heap, right? So that's how dynamic memory works. Like when we create it, so the string, that's what they're doing for us. They create dynamic memory, we're adding to the string, modifying the string. Behind the scenes, they're always taking care of the memory for us. We don't even have to think about it. And that's what they did in the Python class too. When you use the list or the string, then they created a class that allocated memory for you on the heap. You didn't even have to think about it. You were just concerned with learning the fundamentals of programming, okay? So let's see here. So a pointer, and we say pointer num equals, and then the keyword new integer with the value 5, create memory, and then we use memory. Well, here we'll just say value, and we will say we need the value, so we know we need that asterisk, and then we say pointer num use the memory, right? And then we delete the memory. Notice it's a simple concept, but this is a difficult piece. Like, how long will you use the memory? I mean, right now we only have one line of code, so we release the memory. But in reality, programs don't work like that, right? Like, this piece could be like one line of code, one function, two functions, one class, two class. I mean, when do we release the memory? So that's That's why there's a lot of issues out there with memory leaks, right? Where memory is being created and then it's not being released properly. And as the program continuously runs, for example, a web server, if it's releasing memory, then it'll eventually crash because the heap memory, although large, is not infinite. So then when that is exhausted, then eventually the server will crash. So this is dynamic memory. We will use dynamic memory in this class, but not in the tic-tac-toe class, okay? Instead, what I opt to do is I show you how to create memory and how to release memory properly. But right now, since we're focused on the tic-tac-toe application, then you'll just get like quizzes or diagrams or assignments dealing with dynamic memory, okay? So, but all the homework from now on, they'll focus on the tic-tac-toe app. So why won't we use this? Well, because the recommended way of programming in C++ is by using smart pointers, which I've not introduced yet. So smart pointers work kind of like the string and the vector class. Developers have written code that allow us to create memory dynamically, and we create it, we use it, and then C++ takes care of releasing it for us. So the chance for us creating memory leaks are a lot less than if we take matters into our own hand by creating dynamic memory ourselves, right? So before I go into smart pointers, let me remind you how the strings work, okay? So if we have this code, again, this is a refresher because I've discussed this topic before. And then we have the stack, and then we have the heap. And also, this also you will hear it named as the free store or heap, right? Depending on who you're talking to. Okay, so this will be like y something. Okay, assuming JOHN. Okay, so address y46. So if we diagram this, then that's there. First is y46, so we point to the first element in the string. So that's y46, right? This right here looks like a list or an array of a sequence of characters, right? So how did the programmers for the string class, how did they create it? Well, if we think about it, let's go ahead and create the class diagram for the string. Just the name and maybe how they're creating the memory, right? Or not how, what data type they are using to create memory. So we have the string class here, and then they probably have a private pointer to a character, and I don't know what they name it. I'll just name it sequence myself here. So sequence. So then when the class is created, dynamically they create memory for this variable, and then in the constructors they manage the memory. They either create memory for us, and then if say they may allot us 10 free spots initially, and then we exhaust those 10 free spots with pushbacks. So then they write code to detect that we've exhausted the spots. So now they have to create dynamic memory in another location, move this data to that location. Once it's moved, then delete this memory, right? So because they don't want to leak memory. So they do a lot of data management behind this, memory management behind the scenes for us. So once we develop that in-class example for the vector, you will appreciate pointers and dynamic memory, and why I wait till the end of the semester to talk about memory management concepts in this class, right? Because they are difficult. And managing memory will help you become a better developer, but learning how to program, which I focus on for like 3/4 of this class, will make you a better developer. Right? So you don't know how to program, but you know how to manage memory, right? So you have to know how to program and then manage memory, and then you can be a good developer. Okay, so why am I bringing this up? Because I've just said, right, they wrote code to manage memory for us. And we wouldn't even have to think. I mean, we just say string name and we just start pushback and add and calling all different kinds of string functions, and they are doing all the heavy lifting for us, right? So if we go to the agenda, right, that's what smart pointers do for us. The C++ programmers have created a class that allows us to create memory dynamically, and we don't have to worry about when to release the memory. They have code in there to detect with pretty good accuracy when to remove the memory. Does this free us from memory leaks 100%? No, but it greatly minimizes the chances. Okay, so let's go ahead and smart pointers. So there's 3 different types of smart pointers. The unique pointer, where only it can only have like one owner or one reference to it. Shared pointer, it can have more than one pointer pointing to it. And weak pointer, right? I don't talk about smart pointer and weak pointer because this is not a class to discuss those advanced concepts, right? So I stick to unique pointer because it's kind of like only one owner at any one time. And when we create it in main, then main is that pointer's reference or boss, right? Or parent, whatever. If we want to add that pointer, for example, to a vector, now what we are saying is, hey, change the owner from the main region or the main function to a vector. So to do that, we have to use a special function, and that's the move, the stud move function, right? So how do smart pointers work? Well, they work exactly like the string, right? Like, let me, where's my mouse pointer? We create memory, and then that's not it, John, right? So that's not it. Where is it? Well, it looks the same, right? So it creates memory for us, and then we just use it and then forget about it. Eventually it'll be cleared from memory, right? And that's how the string works. Okay, so how do we create this guy? So first we have to include memory header, if I can type, and then we have to include the unique pointer, and then we have to include make unique. Special objects that will allow us to create memory dynamically using the unique pointer. Okay, so unique pointer. So with the vector, we have to specify what data type we are going to store in the list, and the same thing applies to this unique pointer. We say I want to create a unique pointer to an integer, and then we can say unique pointer num equals, and then I can say make unique, and then the data type, and then give it some initial value. And this will create memory dynamically, and the unique pointer will take care of releasing it for me. How do I use it? You use it like any other pointer, right? If we want the value, then we say asterisk and the name of the variable, and then we can go ahead and run that. Let me put a new line here. Okay. And let me go ahead and run this. Okay, so let's see what happened. Okay, so value of 5, so this, right, is the dynamic memory. So we create it, we use it, we release it. But notice with the unique pointer, we simply say, hey, create memory for me, and then I use it, I display the value, and then I'm not worried about deleting it. Unique pointer will take care of that for me, which is what we want, right? We don't want to have to be worrying about memory management unless we are programming like microcontrollers or robotics, right, where memory is very limited. Then this is when this will come in handy. And do not worry, like we will cover about 2-3 weeks of managing memory dynamically, so you should have a good solid foundation to use dynamic memory in the future. Let me see, making sure I'm not forgetting an example. Okay, so far I'm not forgetting anything. I will pause and I will ask if there's questions here. So are there any questions? Like, I know these statements right here may not fully explain, well, why is he making us use smart pointers? But I hope the explanation does, right? Where it's like, well, I mean, we don't want to be worrying about all the rules that I have to know for implementing dynamic memory in functions or classes yet. I mean, working on a tic-tac-toe application itself is difficult, right? Learning the class and structure and all that. So I don't want to complicate it by having you use dynamic memory. Instead, you'll use smart pointers, and you should be okay with them because you use vector and strings, and they're more or less the same. So no questions yet? Okay, so what we can also do is we can ask the address, right? So what is the address about? And let's go ahead and run it. Should have added this. Okay, so address FEEC, so it gets its own address, and we know that the value 100 is so the diagram for the unique pointer, it will look something like this, right? And the value is on the heap, and then there's a stack variable that has the address where that value is stored, right? So there is no difference. The difference will be that the unique pointer takes care of managing the dynamic memory for us, thus eliminating any memory leaks, hopefully, and dangling pointers. Okay, we have one integer. We want to create a vector of integers or a list of integers. We want to add this variable to the vector of integers, right? And we should be able to, because they're integers, right? The only main difference when we create the vector is we have to say create a vector of unique pointers to an integer. So this is what I mean. We have to say, I need to come up here first. And at the vector include. Now I can say, okay, vector, unique pointer of integer type, numbers. Okay, so that creates an empty vector. I mean, there's probably in dynamic memory slots available for us to add unique pointer types. So then we can say, okay, so I know that I can use numbers dot pushback, and then I can say to add this one. And remember what I said earlier. When you create a vector, a unique pointer here, then by default the main region of code is referencing the pointer. What I'm doing now is I'm like, I want to add it to the list numbers, a vector of numbers. Will it let me? So far we know that if we don't have any underscores or red marks, we're okay. But as soon as we try to compile this, we will see that it doesn't like us. And that goes back to what I said. If we create a unique pointer at any one time, only one pointer can point to it, right? So implicitly, the main region of code is pointing to unique pointer. So now we are saying, hey, move to the numbers. It doesn't let us. I said, if we want to do that, we have to use that special stud move function, which behind the scenes is removing the pointer that is pointing to it, and then it has the new vector pointer point to it, right? So that way two pointers are not pointing to it. And then we can say cout value of element 0, and we can say numbers of 0 Why that? Because the vector is storing unique pointers, right? So we know that subscript or the open close bracket gives us a first element, but that first element is a unique pointer. So then if we want to get the value, then we use the asterisk, and that should give us the value, and the value should be 100. Okay, so let's see. So notice the error is gone. We moved it into the vector, which in essence invalidated this guy. This pointer here was invalidated with move, so we have to be aware of that. Like, this will be a pointer that points to nothing. Instead, now it's in the vector, right? So meaning we cannot use it after line 54. Okay. Any questions? If it terminates the memory midway through the program execution, what does that mean? It terminates the memory midway through the program execution. Well, it's not going to clear the memory unless it's used in different situations. And if you recall how integer works, when you create an integer in a function, that integer lives in that function only. Once that function terminates, then that integer is gone. That's the functionality that unique pointers give us. Even if we don't call delete, when the function exits, in essence, that pointer is removed from memory. If we create it in a class, as long as the class is alive, that unique pointer is alive. Once that class is removed from memory, then the unique pointer is removed from memory, just like private data members that are simple types like integer or double. If we create dynamic memory in a function and we forget to call delete, we already leaked memory. Because we created, we used it, but we didn't delete. So that's the power of unique pointers. They leave the memory management to C++. And as beginning programmers, yes, we want to learn how to manage memory, but it's also good that, hey, I can have unique pointer as long as I'm not limited in memory. And you shouldn't for most of the time, right? Unless, like I said, you're creating like device driver code, microcontroller code, robotics code like for NASA, Mars rover or something like that, then memory is very limited. So then you have to be an expert at managing memory. Yep. Okay, so that's all I want to cover today because that's as much as I covered for yesterday's class. Let me go ahead and stop.